Hello, my name is Carol Leibel, and today we're going to examine standard deviation and its importance in AP Biology. Now, let's suppose that you are collecting data and you know that repetition is extremely important. And you want to know how much variation is in your data and whether it's significant or not. So a statistical computation that measures how far members of a population, or data points, if you will, deviate from your mean is called the standard deviation. Standard deviation, in other words, is how much spread there is in your data. It's the characteristic of a population, so it doesn't depend on how many data points or how many members you have unless you don't have a good sample size. Then you won't get a good estimation of standard deviation. All right, so throughout this discussion of standard deviation, we're going to be referring to these two histograms. And so I want you to take a minute, pause the screencast, and see if you can make any comparisons between the two, how they are alike and how they are different. Go ahead and pause it. All right, so you've paused it, and hopefully these are some things that you found. You should have seen that both histograms have a mean of 5. However, one of the big differences between the two is that there's more variation or more spread in the data forming histogram number 1. In fact, the range is 8 units, whereas in histogram number 2, the variation is less, or the spread is less, and so the range there is only 5 units. One way that both these histograms are alike is that the data is distributed normally, or it forms a normal distribution, or that nice bell-shaped curve. Now, it turns out that there's a way to kind of measure that variation, and it's called the standard deviation. So, mathematically, the way you determine the standard deviation is, first off, you have to determine the mean for your data. Secondly, once you do that, you have to find the difference between each data point and the mean. And then once you do that, you're going to square that difference. Once you have squared all the differences, you're going to add them all up. All right, and in the formula, that means to sum it. And then you're going to divide it by the number of data points less 1. So if you use 10 data points, you would divide by 9, or if you used 100, you divide by 99, and so on. And then last, you're going to take the square root of that number. On your formula sheet, on the front page in the upper left-hand corner, there's the formula for standard deviation. Now, on the AP exam itself, you will not have to determine the standard deviation. They may give it to you, and you may be asked to apply that value in some sort of situation. So now it's your turn. I want you to pause the screencast, and I want you to determine the standard deviation for this data that measures the height of 5 beans. So go ahead and pause it. All right, well, welcome back. So remember, the first thing you're going to do in determining the standard deviation is you're going to find the mean of your data. So you're going to add it all up, and in this case here, we see that the value is 40. We're going to divide it by 5 data points, and so our mean is, and actually this should be, never mind, our mean is 8. So now what we're going to do is we're going to take 10 minus 8, and we know that's 2. We're going to square it, so that value is 4. 7 minus 8, we know that's going to be a -1, but when we square it, we'll get rid of the negative sign. 6 minus 8 will be a -2, and when we square that, get rid of the negative sign. And then 8 minus 8 is 0. And then 9 minus 8 is 1, and we're going to square that, and it's going to be 1. So the next thing we have to do is we're going to add these up now, and we're going to find that our value is equal to 10. The next thing we have to do is we're going to divide it by n minus 1. So we had 5 data points. N minus 1 would be 4. So that's going to be equal to 2.5. The last thing we're going to do is take the square root of our value. The square root of 2.5 is going to be equal to approximately 1.6. And that's what you should have come up with when you determine the standard deviation for these beads. So what that means is that on the average, the data points were off by 1.6 centimeters. And here it is, typed out nice and neat for you. All right, so let's go back to our 2 histograms. And it should not surprise you that histogram 1 has a greater standard deviation than histogram 2 because there's more spread in the data in histogram 1. So that makes sense. Okay, and remember they both have the same mean of 5. Now, some interesting facts about standard deviations and normal distributions. It turns out that the percentage of data points that fall within plus or minus 1 standard deviation is 68.26%. And the percentage of individuals falling within plus or minus 2 standard deviations is 95%. And 3 standard deviations is actually 99.7%. Just not 99, but 99.7%. So this is often called the 68, 95, 99 rule in statistics. So let's go back to our examples and see what that would look like. All right, so in histogram 1, we said that the standard deviation was 2.053, that's equal to 1 standard deviation. The mean was 5. So to determine where the boundaries for 68% would fall is that would be 5 plus 2.053, and that would be equal to 7.053 over here for this boundary, and then 5 minus 2.053, and that would be over here for that boundary, or 2.947. Okay? All right, so for 2 standard deviations, it would be, you would take 2.053, multiply that times 2, and that would be 0.4106. And so 5 plus 4.106 would be equal to 9.106. And then 5 minus 4.106, and that would give you 0.894. All right, so 95% of all the data points are going to fall between 9.106 and 0.894. Now in histogram 2, our standard deviation is smaller. Our standard deviation is 1 standard deviation is equal to 1.046. And so if you're going in 1 standard deviation above would be 6.046 and below would be 3.9454, and then 95%, which would be 2 standard deviations, would fall between 7.092 and 2.908. Remember what the standard deviation is illustrating is that it's illustrating how much spread is in the data, how much variation is in the data. There's more variation in data set number 1 than in data set number 2. So now we have some application of this. A student was measuring the height of mung beans. The height of the mung beans of 200 mung beans was measured. The mean height of the mung beans was 4 centimeters, and the standard deviation was 0.5 centimeters. And the other thing they should mention to you is that the data was normally distributed. What percent of the plants had a height between 4 and 4.5 centimeters? What percent of the plant had a height between 3 and 4 centimeters? So pause the screencast so that you can work on this problem. All right, so the thing we need to know is that it formed a normal distribution. So we're just going to go ahead and draw a normal distribution. And we're going to say now that that being the case, it says that the mean was 4 centimeters, and the standard deviation, one standard deviation was 0.5. So now if I go out to 4.5, and I go in this, that would be positive 1 standard deviation. And if I go out here to 3.5, that would be minus 1 standard deviation. And that we know that plus or minus 1 standard deviation, that 68% of all the data points fall within there. But what we want to know is we want to know how many plants fall between right here. Okay, and so that would be plus 1 standard deviation, which would be not 68%, but 1/2 of that, which would be 34%. So 68.34 times 200 plants would be equal to 68 plants should fall between 4 and 4.5 centimeters. Now it says what percent of the plants had a height between 3 and 4 centimeters? Well, 3 and 4 centimeters would be way out here. And we know that, again, 1 standard deviation was 0.5 centimeters. So if we go out 1 centimeter, which would be 5 here, and 1 below, which would be 3 here, we know that that would be minus 2 standard deviations, and this would be plus 2 standard deviations. And if we want to know how many plants were between 3 and 4. So now we're over here on this side, but this time we're going to measure all of these. And we know that 2 standard deviations would be 95% plus or minus 2 standard deviations. So, but we only want half of that. So we have 95% be equal to 2 standard deviations. Half of that, because we're only doing between 4 and 3, would be 0.475 times 200 plants, would mean that there should be approximately 95 plants that would fall between 3 and 4 centimeters. All right, so let's try another question. A student is germinating lettuce seeds in a petri dish, and after 3 days, 95% of them are between 1 and 1.1 centimeters and 1.7 centimeters long. Assuming that the data is normally distributed, determine the mean and the standard deviation. All right, so again, we're assuming a normal distribution. All right, and so it says that 95% is between 1.7 and 1.1, and that would be 95%. But we also know that 95% means that would be plus 2 standard deviations in that direction and minus 2 standard deviations in that direction. Now, to determine the mean, it's pretty easy. We're just simply going to we just want to know the value that's right in the middle. So 1.1 plus 1.7 is equal to 2.8. And what we want to do with that is divide that by 2. So our mean is going to be equal to 1.4. So we're going to put a 1.4 right up there. All right. So now what about this standard? What's one standard deviation, or the standard deviation? So what we can do then is we can say that we can take 1.7 and minus 1.1 is equal to 0.6. And so we would have 2 standard deviations above and 2 standard deviations below. So if we divide that by 4, that's going to be equal to 0.15 for one standard deviation. All right, so let's go on to that next one. A student is measuring the mass of pill bugs and finds that 99.7% of the mass of the pill bugs fall between 0.034 grams and 0.18 grams. Assuming that the data is normally distributed, determine the mean and the standard deviation. All right, so again, we're just going to make it's normally distributed. And so we know 2 values. And the 2 values that we know is over here on this end. We know that's 0.18 grams. And over here on this end, it's 0.034. And that we have captured between those 2 values 99.7% of all the data points fall between those 2 values. So what is the mean? Well, we can find the mean the same way we found the other mean. We can take 0.034 plus 0.18. That's going to be equal to 2.214. And we're going to simply divide that by 2. And so our mean is going to be 0.107. Well, what's the standard deviation? Well, this time we know that that is plus 3 in that direction and minus 3 standard deviations in that direction. And so if you take 0.18 minus 0.034, and that will be equal to 0.146. And remember, 3 above and 3 below, so that's going to divide by 6 now. Our standard deviation is equal to 0.024. So these are some problems that are asking you to apply the concept of standard deviation to different data analysis. So here's another example, pinto beans and black-eyed peas. It says, shown are the histograms illustrating the frequency distribution of the mass of 300 black-eyed peas and 300 pinto beans. So pause this for a second, see how they're alike and how they're different. Okay, welcome back. Hopefully what you determined is that the pinto beans form a really nice normal distribution. The black-eyed peas, it's a little bit skewed, but okay, we'll have to deal with it. They do indeed have different means. There's more variation in the data with the pinto beans than the black-eyed peas. And so it should not surprise you that their standard deviation for the black-eyed peas was only 0.042, but almost twice as large in the pinto beans, 0.074. Now, is it possible, and it is, to compare the means of the two populations using a simple bar graph? And we could do that. We could take a little bar graph and we could put the means. This would be the mean of the black-eyed peas, and this would be the means of the pinto beans. But now it's like, okay, but look, we've got all this variation, and we would like to show that pinto beans has more variation in their data than the black-eyed peas. So the way we could illustrate that vertically is using something called an error bar. So the way that you would insert an error bar is that you would add the standard deviation above and then minus the standard deviation below. And so there are different kinds of error bars, but this is an error bar that is representing the standard deviation. All right, so this is what your bar graph would start out looking like. It would be illustrating the mean and the grams, okay? Now we want to put in our error bars. And so in this case here, we want to go 0.042 above and 0.042 below with our black-eyed peas. And then we want to do the same thing with our pinto beans. And our pinto beans, our error bars are going to be a little bit larger because there's more variation there. And so when we do it, this is what it actually would look like. This is a bar graph illustrating the means of black-eyed peas versus pinto beans, and we're using standard deviation error bars to illustrate the variation in those different beans. And what it's basically saying is that pinto beans has more variation in their mass than black-eyed peas. That's all it's showing. And again, I want to emphasize that there are different kinds of error bars. And in the next PowerPoint, we're going to be looking at what we call standard error of the mean error bars. And this is what they would, this is what they're going to look like. And we're going to explain that concept in the next PowerPoint. So if you have any questions, my name's Carol Leibel again. There's my email address, and just email me and I'll write you back. Take care. Talk to you later. Bye.